Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, so for this video is to cover topic 6, which is the matrices and system of linear equation. Okay, so firstly we will go into 6.1 about matrices. Okay, for the learning outcome, at the end of the lecture, students should be able to identify the different type of matrices, perform operation on matrices which include the addition, subtraction and multiplication, and then define the transpose of a matrix and use the properties. Okay, so by the definition, a matrix of order m by n is a rectangular array consisting of entries m horizontal rows and n vertical column as shown below. So it just means the row and column that we have in a matrix. Okay, so A11, A12 and AMN are the elements of the matrix, which is the component in the matrix. So a matrix is called m by n if it has number of m rows and n column. Okay, we start by mentioning the number of row and then followed by the number of column. Okay, and then a matrix for which the entry is in row I and in column j is denoted by Aij. Okay, so Aij also means the row and column that we have in our matrix. Okay, an expression m by n is called the order of the matrix. Okay, a matrix with only one column is called column matrix, and then a matrix with only one row is called a row matrix. Okay, so let's proceed to the type of matrices. Okay, so firstly we have a square matrix. Okay, what is a square matrix? A square matrix is a matrix with an equal number of rows and column in a square matrix. So just like a shape of a square lah. So we have same length, same number of row and same number of column. For example, this A matrix A is a 2 by 2 matrix. Okay, which means it has 2 row and also 2 columns. Okay, then for matrix B, this is a 3 by 3 matrix which consists of 3 rows and 3 columns. Okay, if the matrix has the same number for row and column, so that is called as a square matrix. Okay, for zero matrix, a matrix with elements that are all zeros. Okay, for example, this is the example. So a zero matrix does not necessarily to be a square matrix. Okay, square matrix means the size of the matrix. Okay, then for a zero matrix, it indicates the component inside of the matrix or the element of the matrix. All of the element must be equal to 0. For example, we have matrix A, matrix B and matrix C, which are all consist of all element of zeros as the element. Okay, then we have a diagonal matrix. A square matrix is where all the elements are 0 except the elements in the principal diagonal. Okay, for example, we look at this matrix A. Okay, matrix A is a 2 by 2 matrix. Okay, and the elements is 2 0 0 3. As we can see that 2 3, see, this is called as the diagonal inside the matrix. Okay, this 2 3 is the only element which are not 0 in the matrix. So if this situation happens, so this A, matrix A is called as a diagonal matrix. And also for matrix B, as we can see the diagonal of the matrix. Okay, I show you with my pointer. 1 2 3 is in the position of a diagonal, and these elements in the diagonal are the only elements that are not 0 in this matrix. So this is a diagonal matrix. B is a diagonal matrix. And also for C, okay, even though one of the element in diagonal is a 0, but as long as we have A and B which are not 0, so the C is also called as a diagonal matrix. Okay, next we have identity matrix. Okay, identity matrix is a matrix with all entries in the main diagonal are 1 and others are 0. Okay, also related to diagonal of the matrix. Okay, as we can see for matrix A, we have 1 0 0 1. The diagonal is 1 1. Okay, only 1 at the diagonal, and for the other parts are 0. Okay, then for B, we have 1, 1, 1 at the diagonal and the other elements are 0. So if this situation happens, the matrix is called as the identity matrix. Okay, next we look at a lower triangular matrix. Okay, lower triangular matrix, a square matrix where elements A, I, J for 0 for I is less than J. Okay, I is less than J, which means the number of row, okay, the number of I must be less than the number of column. For example, you can see here, for lower triangular matrix, the elements that are not 0 is situated in the shape of a triangular at the lower part of the matrix. Okay, and then for matrix B is also the same thing, located at the lower part of the diagonal. So that matrix is a lower triangular matrix. Okay, then for upper triangular matrix, okay, the element which are not 0 is situated at the location of the upper region of the diagonal, 1, 2, 3, 2, 4 and 3. Okay, and also for matrix B. Okay, next we look at equal matrix. Okay, what does we call equal matrix? Two M&N matrices are equal if they have the same dimension. Okay, must have the same dimension and their corresponding entries are equal. Okay, there are two conditions here. Must be the same dimension and corresponding entries are equal, which also means the elements of the matrix. Okay, for example, we have matrix A, matrix B, matrix C, D, E and F. Okay, which matrices below are the same? Okay, let's identify. Okay, you can see that for matrix A is a 2 by 2 matrix. Okay, so in order to find another matrix that is the same as matrix A, we have to focus on matrix that is also in the size of 2 by 2. Okay, for matrix D, okay, because matrix B and C are 1 by 2 matrix. Okay, for matrix D and matrix E are the only 2 by 2 matrix other than A. So we have to compare matrix A and with matrix D and E. Okay, as you can see, matrix A is 1, 2, 2, 1. Okay, and for matrix D, the element is 1, 2, 2, 1. So the size of the matrix is also the same. Then the entries of the matrix is also the same. So we can conclude that A is equal to D. Matrix A is equal to matrix D. And if you want to compare matrix A and matrix E, even though the size of matrix is the same, a 2 by 2 matrix, but the entries of the matrix are not the same. Okay, for E it is 2, 1, 2, 1, so it's not the same. So A is not the same as matrix E. Okay, so that's all for the first part, the types of matrices. Okay, so next we move on to 6.1.2 about operation of matrices. Okay, so firstly we look at addition and subtraction of matrices. Okay, so mention here that we cannot define matrix addition or subtraction unless the matrices are in the same order. Okay, so that means the size of our matrices that we want to do the operation of addition and subtraction must be in the same size. Okay, for example, let's give you a matrix of A, which is 2, 3, 4, 1, 0, 5, and matrix B of 4, -2, 3, 1, 1, 4. Okay, so now let's say if I want to make matrix A plus matrix B, so in order to do this operation of addition between these two matrices, first we must identify whether A and B are in the same order. So for matrix A, the order is 2 by 3 matrices. This is a 2 by 3 matrices. And then for matrix B, it is also a 2 by 3 matrices. Okay, so then since this order of the matrices is the same, so then we can proceed with the operation of addition. Okay, so in order to do the addition, the element, the position of element in the matrices must be done with the operation that we want to do. Okay, for example, we want to perform addition. So that's mean for the element at the first row and the first column, which is 2, okay, 2 from A must be added with the element also at the same position from element B, which is 4, that is in the position of the first row and the first column. So 2 plus 4. Okay, so next, for the number 1 right here, which is from the second row first column, 1 must be added with the same element also from the second row and the first column, 1 plus 1. And so also for the other elements, so 3 plus negative 2, 4 plus 3, 0 plus 1, and also we have 5 plus 4. Okay, so that is the method to do the addition. Okay, so then we calculate the answer for each element. So now we have 6, 1, 7, 2, 1, and 9. Okay, so this is the answer for addition between matrix A and matrix B. Okay, so the same concept also applies for operation of subtraction. Okay, let's say if you want to do A minus B, okay, firstly we check whether the size or the order of the matrices for matrix A and B are the same. Okay, we already verified that both are in the same size. So to perform subtraction, the first element, which is the from the first row and the first column from matrix A, minus the element from the first row and the first column from matrix B. So we have 2 minus 4, 1 minus 1, 3 minus negative 2, 0 minus 1, 4 minus 3, and 5 minus 4. Okay, so now we do the calculation. Right here we have negative 2, 0, 5, negative 1, 1, and also 1. So this is the new matrix form from the operation of subtraction in between matrix A and matrix B. Okay, next is the scalar multiplication. Okay, mention here if C is a real or complex number and we have matrix A that has the element of Aij, then if we have C right here, which is the scalar that multiply with matrix A, okay, which means C is just a number, not a matrix, multiply with a matrix equal to Bij. So mention written here that Bij is actually equal to C multiplied with Ij. Okay, so for example 6.3, we want to compute negative 1 over 2 dot matrix 3 by 2 matrix. Okay, we can see that the negative 1 over 2 is actually the scalar and multiply with a matrix. This is a matrix. Okay, so what we do is we take the scalar and we multiply it with each of the elements inside the matrix. Okay, for example, you can see here we take the negative 1 over 2 multiply with 2, okay, then we have right here negative 1 over 2 multiply negative 4, 8, 5, negative 6, and 7. Okay, we take the scalar and multiply it with all of the elements inside the matrix. Okay, so this is the operation right here. So negative 1 over 2 multiply 8, negative 1 over 2 multiply negative 6, and then we have the final answer. So this is the answer for scalar multiplication within a number and a matrix. Okay, so just now we have discussed multiplication between a scalar and matrices. Okay, now we want to look at about multiplication of two matrices. Okay. Okay, in order to do multiplication of matrices, there are a few conditions or a few situations that has to be met, because not all type of matrices can be multiplied. Okay, so for example, let's say we have matrix A and matrix B. Okay, the matrix A is a 2 by 2 matrix, and meanwhile matrix B is a 2 by 3 matrix. Okay, so the first condition, in order for us to multiply matrix A and matrix B, is we have to check whether the inside number, which is these 2 and these 2, are the same. Okay, if 2 and 2 are the same, okay, these two number are the same, so that means it can be multiplied. A and B can be multiplied. Okay, if the number are different, for example, if I give you matrix C and matrix D, matrix C is a 2 by 3 matrices, and meanwhile matrix D is a 2 by 1 matrix. Okay, so as you can see here, the number 3 and number 2 here are not the same. Not same. So then C cannot be multiplied with D. Okay, so that is the condition. That is the first thing, the thing that you have to give focus on. Okay, then since A and B now can be multiplied because the number 2 are different, okay, then the multiplication we produce a new matrix. Okay, A and B, we create a matrix, for example, matrix P. Okay, we call it a matrix P. So what is the size of matrix P? What is the what is the number of row and the number of column for matrix P? Okay, that can be easily be determined by referring to the outside number, which is the 2 and the 3 right here. So the 2 and the 3 indicates the number of row and column that will be formed with our new matrix. So we have 2 and 3, so that means the multiplication between matrix A and matrix B will create a 2 by 3 matrix. Okay, so that means our matrix P is a 2 by 3 matrix. Okay, so now let's look at an example. Let's say I have a matrix A that is 1, 2, 1, 3. Okay, matrix A 1, 2, 1, 3, and I have a matrix B equal to 1, -1, 0, and 2. Okay, so I want to find the multiplication of matrix A and B. Okay, so firstly, by referring to the the condition that I have told you, we have to identify whether the matrix A and matrix B can be multiplied or not. Okay, then we check. Matrix A is a 1 by 4 matrix. Okay, because it has 1 row and 4 column. And for matrix B is 4 by 1 matrix. So in order for us to multiply A and B, so matrix A and matrix B, so matrix A is 1 by 4 and matrix B is 4 by 1. So from the inside number 4 and number 4 right here are the same. So it can be concluded that matrix A can be multiplied with matrix B. And what is the size of our new matrix? The size of the new matrix will be based on the outside number 1 and 1. So it will form a 1 by 1 matrix. Okay, so now let's try to do the multiplication. So it will be 1, 2, 1, 3 multiply with matrix B which is 1, negative 1, 0, and 2. Okay, what we need to do here is we multiply each element from the row with each element from the column of matrix B. Okay, for example, the first element, which is 1 from the row of matrix A, we multiply it with the first element of the column from matrix B. So it will be 1 multiplied with 1. Okay, then we plus it with the second element from the row of matrix A, multiply with the second element from the column of matrix B. 2 multiply with negative 1. Okay, then we plus with another 1 multiply with 0 plus 3 that multiply with 2. Okay, so then we close our matrix. So from here we have 1 minus 2 plus 0 plus 6. Okay, so from here we have our new matrix that is equal to 5. So 5 is the only element in our matrix that produced from the multiplication between matrix A and matrix B. So 5 is a 1 by 1 matrix. So it follows the condition that we have mentioned before. Okay, now let's continue with more example. Okay, now we want to look at multiplication of matrix B and matrix A. Okay, I will give you the matrix A. Here is 1, 2, 1, 3. Okay, so now we want to find. Before this, we did A-B, multiplication of A and B. So now we want to do B-A. Okay, as you can see, it will give you a different answer. Okay, for B-A is not the same as A-B. Okay, so B is a 4 by 1 matrices, and meanwhile A is a 1 by 4 matrices. Okay, so firstly we check either these two matrices can be multiplied together. So it is 1 and 1 from the inside number, so that means it's the same, so it can be multiplied. Okay, so from the multiplication, it will give you a new matrix with the size of 4 by 4. Okay, so now we have a bit clue or hint for our answer. So now we proceed with the procedure. So B is 1, negative 1, 0, 2. And for matrix A is 1, 2, 1, 3. Okay, so the same concept also applies here. All of the element from the row of matrix B multiply with all of the element from the column of matrix A. So that means we should have 1 multiplied with 1. So that comes from the first row and first column, and it will be the new value for first row and first column of the new matrix. So 1 multiplied by 1. Okay, so for the second column, for the second row, for the first column, which is the multiplication of negative 1 and 1. So negative 1 and 1. So next is 0 and 1. Next is 2 and 1. Okay, so now we have done for our first column. Okay, for the second column, all of the element from row B multiply with the second column for element from matrix A, which is 2. So now we have 1 multiplied by 2, negative 1 multiplied by 2, 0 multiplied by 2, and we have 2 multiplied by 2. Okay, so the same thing we do for the rest of the elements. So next we have 0, we have 1 multiplied by 1, negative 1 multiplied by 1, 0 multiplied by 1, and we have 2 multiplied by 1, and then for the final column we have 1, 3, negative 1, 3, 0, 3, and we have 2, 3. Okay, so now we complete the calculation, and we will have 1, negative 1, 0, 2, 2, negative 2, 0, 4, 1, negative 1, 0, 2, and also we have 3, negative 3, 0, 6. Okay, so this is the answer from the multiplication of matrix B with matrix A. Okay, as we can see, we observe that the new matrix form is a 4 by 4 matrix. Okay, the same thing as mentioned before. Okay, so now let's try if you want to multiply matrix B and matrix C. Okay, so for matrix B and matrix C, so we know that matrix B is 4 by 1 matrices. Okay, and matrix C is 2 by 4 matrices. Okay, so from the inside number we have 1 and 2. So these two numbers are not the same. So that's mean matrix B and matrix C cannot be multiplied together. But however, if we do for multiplication of matrix C and B, which is 2 by 4 and 4 by 1, the inside number 2, 4 and 4, these two numbers are the same, so it can be multiplied. So if we produce 2 by 1 matrices, 2 by 1 matrices. Okay, so now let's prove that. So matrix C is 2, 1, 0, 1, 0, 1, 1, 3, and B is 1, negative 1, 0, 2. Okay. Alright, so for the multiplication, we have first row from matrix C multiply with the column from matrix B. So 2, we have 2, 1, plus 1 and negative 1, plus 0 and 0, plus 1 and 2. Okay, so that is from the first row and the first column. Okay, now let's do for the second row and the first column. So 0 and 1, plus 1, negative 1, plus 1, 0, plus 3, and 2. Okay, we close the matrix. Okay, so we do the multiplication and perform the addition. So we should have a new matrix of 3 and 5. So this 3 and 5 is a 2 by 1 matrix which consists of 2 rows and 1 column as proven from here. Okay, let's look at one example of question. Find a matrix A such that A multiplied with another matrix 0, 1 to negative 1 that is equal to 2, 1, negative 1, 0. Okay, notice that the question mentioned that the A is actually a matrix. Okay, A is not a scalar. So means we need to know the size of the matrix before we can identify what is the element of the matrix. Okay, so based on the rule that we did before, okay, so we know that A multiply with a matrix. Okay, let's label the matrix as B. Okay, we didn't know what is the size of matrix A and just mark it as M by N. Okay, we make it as M by N. But for matrix B is well known is a 2 by 2 matrix. Okay, so multiplication of these two matrix produce a matrix C. Okay, just label it as C. And then the size of the dimension of the matrix C is a 2 by 2. Okay, so that's mean A multiply with matrix B and it produce a matrix C. Okay, so in order for the multiplication can be done, the inside number must be the same, which is N and 2 must be the same. Only by that matrix A can be multiplied by matrix B. So automatically we can say that N is actually equal to 2. Okay, So since this is this multiplication produce matrix C with a dimension of 2 by 2, so that's mean M, the outside number M and 2 must also produce a 2 by 2 matrix. So then we know M is equal to 2. So we can conclude that matrix A is a 2 by 2 matrix. So for now, for the elements, we just put entries of A, B, C, and D, and make sure it is a 2 by 2 matrix. Okay, so in order to find the element of A, B, C, and D, okay, so now we will have A, B, C, and D, which represent the matrix A, and then for matrix B, 0, 1, 2, negative 1, that is equal to 2, 1, negative 1, 0. Okay, so from here, we perform the process of multiplication between A and B on the left side, and we will have A that multiplies 0, A multiplies 0, plus B multiplied with 2. Okay, and then for the first row, second row, first column, we will have C multiplied with 0 plus 2 multiplied with D. Okay, so this one we will have A 1 plus B negative 1, and we have C 1 plus D negative 1. Okay, close the bracket, and this is equal to 2, 1, negative 1, and 0. Okay, so now we calculate the left side, and we will have 2b is 0 plus 2b, 0 plus 2d, A minus B, and we have C minus D. That is equal to 2, 1, negative 1, 0. Okay, now what we need to do is to find the value for A, B, C, and D. Okay, we can do the equation. The element in the first row, element at 1, 1, okay, row number 1, column number 1, must be equal to the same position on the right side. So 0 plus 2d will be equal to 2. So we can say d is equal to 1. Sorry, that is not d. 0 plus 2b equal to 2. Okay, so then we have b equal to 1. Alright. Okay. Okay, then we have 0 plus 2d must be equal to negative 1. So d equal to negative 1 over 2. Okay, and then next for A minus B must be equal to 1. A minus B equal to 1. We have already found the value for B. So A minus 1 equal to 1. So A equal to 2. Okay, and then for C minus D equal to 0. So C minus D equal to 0. And C minus negative 1 over 2 equal to 0. So C equal to negative 1 over 2. Okay, now we can say that matrix A is equal to 2, 1, negative 1 over 2, and negative 1 over 2. So that is our final answer. Okay, for transpose of a matrix, okay, the transpose of a matrix n by n matrix A is the n by m matrix AT. Okay, the small t indicates the transpose obtained by interchanging the row and columns of matrix A. That is, the ith column of A transpose is the ith row of A for all I. The properties of the transpose of a matrix. Okay, this box shows the properties of a transpose. Okay, the first property is that, let's say if we have a transpose of a matrix A and we transpose it one more time, then we will have the original matrix of A. Okay, and if we have A matrix A plus B and we transpose the answer from that, is just as equal to A transpose plus B transpose, and also the same thing applies for subtraction. Okay, so next, if we have AB transpose, also as the same as B transpose A transpose. Okay, notice that it starts with a letter, with a matrix B transpose first, then followed by A transpose. Okay, then if we have a scalar multiplication of A, and then we want to transpose the matrix, is just as the same as K A transpose, because K is a scalar, so there is no transpose for a scalar number. Okay, so let's look at an example. Alright, transpose is actually an easy process. Okay, let's say we have a matrix A, a 3 by 3 matrix, 1 2 3 0 1 2 7 5 9. Okay, so now let's say if you want to find the transpose of this matrix, so we write down A with a small t, which indicates the transpose. Okay, so notice that this is the first row. Okay, I write it down as row 1, row 2, and row 3. Okay, to do the process of transpose, okay, we choose the first row and make it as the first column. Okay, so that it will be 1 2 3. Okay, this 1 2 3 comes from the element of the first row of matrix A. So we write it down in the arrangement of a column. Okay, then we follow by the next row, row number 2, that will become the second column, 0 1 and 2. Okay, then the third row will become the third column, 7 5 and 9. Okay, so that is our transpose for matrix A. Okay, as you can see, the diagonal is not changed, 119, and the original one is also a 119. Okay, maybe that is enough explanation for transpose, because later we'll be using this in another operation. Okay, a little bit more about transpose, a symmetrical matrix of matrix A. Okay, let's say if we have a square matrix of matrix A is symmetrical if it is equal to its own transpose. Okay, as you can see, for example, if we have matrix A, a 2 by 2 matrix, and the elements are 1 2 2 3. Okay, as you can see, the upper triangle is identical to the lower triangle. So if we transpose this matrix A, we have AT equal to 1 2 2 3. So it is identical. Okay, so since matrix A is identical to its A transpose, so the matrix A can be called as the symmetrical matrix. Okay, so the same thing also applies for example for matrix B here. As you can see, the elements in matrix B is 1A negative B, A3C negative B, C2. So if we do the transpose in this matrix, so we still have the same arrangement of elements in matrix B transpose. So matrix B is also a type of symmetrical matrix. Okay, also written here in a symmetric matrix, the elements are symmetrical about the leading diagonal. Okay, next is about skew symmetrical matrix of matrix A. Okay, let's say we have a square matrix of matrix A equal to Aij is a skewed symmetrical matrix if matrix A is equal to its negative of A transpose. Okay, for example, we have a matrix A that is equal to 0 to negative to 0. Okay, if we do the transpose of this matrix, so it will be equal to 0, negative 2, 2, 0. Okay, 0, negative 2, 2, 0. Okay, then if we multiply this A transpose with a scalar of negative 1, so you can see there the symbol of negative in front of the matrix, then it will be equal to 0 to negative to 0, which is just as equal to the original matrix of A. Okay, so if this situation happens, the matrix A is a type of skew symmetrical matrix. Okay, if the transpose is equal to the negative, okay, a negative A transpose is equal to the original A matrix.